New Guinea. And also, Dr. Garber was a research associate in the Institute of Applied and Inorganic Chemistry at the University of Hamburg, and postdoctor at the Department of Material Science in Regional National Laboratory in Roskilde, Denmark. And he was a research assistant at the University Hospital Essen and the Institute of Medical Radiation Physics. And also he was a medical physics expert at the Radiological University Clinic Bonn, and also senior medical physics expert at the Radiological University Clinic Bonn. And also he was a medical physics expert in the Radiological University Clinic Bonn. And also present, he is working today as a leading medical physics expert in the clinic for diagnostic and interventional radiology, deputy senior medical physicist in the clinic for radiation therapy and radiation oncology. And also Dr. Garber is a professional member of DGMP, DPG, and DEGRO, also ESTRO. Sir, over to you. So you can start the lecture.
Please unmute yourself. You are muted.
So very much, Mrs. Jayakori, for the very nice introduction. And I'd like to welcome all the listeners, students, and collaborators, colleagues from this course. And I would like to give today an overview on image quality control in interventional radiology. So, as those who had listened to my talk about quality control in conventional radiology, we now skip to an area where quality control has definitely a little bit different approach. Of course, the quality control in interventional radiology should follow all legal requirements, but the legislation is required. So it is important that the quality control already starts as in conventional radiology with commissioning as the acceptance test, or and after the first after a major upgrade or a breakdown of the machine. Very important is that during acceptance test and during commissioning, you have to define a baseline, which is the baseline for your entire quality control you have to follow during the lifetime of your machine. I would recommend for a simulation or optimization, you all have set up a program where you can test different parameters. We will come to this later on. The major issue for interventional radiology, as more as for the others, conventional radiology, is what are the reference conditions and do they match the clinical situations? The problem is you have to separate your quality assurance into a reference part, which is the imaging system, and then something which called the real-time task. So something like a clinical situation. That's definitely different to what we have learned in quality control for conventional radiology. The quality control should enable a reasonable image quality at a justified dose level. That's something which is general written over above every quality control, and you really have to stick to your reference values. We will come to the reference values for the ER, for the interventional radiology later on. But now, with interventional radiology, you really have to test. I would call it an end-to-end test. You really have to test your entire imaging chain, and you have to look whether with all the parts of this imaging chain does the patient dose is okay, and do you still have an acceptable image quality? That should be your major aim above everything. So what are the other requirements? The next requirement is reproducibility. All your tests should be somewhat reproducibility. I will show you some setups which are used among the EU. Maybe you can follow those to see how robust they are. And the second thing you have to think is, does a static measurement is enough to match a dynamic situation? This question will follow us the entire talk. We still have to consider ourselves, does a static measurement, so static conditions, recover a dynamic situation, what we do in interventional radiology? Do we have to separate into a static imaging or in linked imaging? So do we just check the entire system while moving, or do we have separate the Xray tube and then test the detector separated, or do we have to link them? That's something. What is good clinical practice in interventional radiology? A very interesting part, you can look it up. If you look into literature, you will find a lot of interesting publications. But what is the goal? What is your goal, actually? Quality assurance should guarantee the quality at a reasonable dose. That's what is the right dose? So again, I will show you some helpful guidelines which give you the right dose. Important part is that you have to test all. I would like to stress that all parts of the imaging chain should be tested, but you will find that not for all parts there exists some kind of reference levels. And does all these tests predict the patient dose? That's also something we have to consider during our talk today. Can we improve something? Do we have to add tests or replace tests after we figured out after a year that we really do not see something we would like to see? And the very most important part, do we work close enough to clinical practice? Do we work close enough? Even though there are standard references, standard tests, is our clinical practice close to that what we are testing? For example, if we are in cardiology, angiography is placed and we have a moving heart. Does the moving heart really is covered by our test procedures for air dose camera or entrance dose or quality, image quality? Is it really matched by that? Or do we have to do some thrombectomy or some other angiography of extremities? So, you know, there are several questions we have to look if this match our system. Better clinical practice, could do better? That is always something we have to ask ourselves again. Could we do it better? And I will show you something where we maybe get helped recently. And you see that the manufacturers usually does monitor the dose, which are then given into a dose structured report. And these are the values which are maybe given also to the authorities during quality control. Are these data linked to our data? Do they match all these? This is another question we have to solve. So what are the specific requirements of your system? The first thing is you have a complex dynamic imaging. You have to have a procedure time, acquisition time, fluorescent times, which may differ. Do you use contrast media? And what are the beams of view? So what angulation of the system do you use? And you really have to look if all the images at all time match your dose. Or does the dose be extended while you're doing maybe a triggering of the heart, or you do a vital monitoring if that's already done? And then another problem is you have to ask the operator who's actually, or the interventionalist who is actually doing the procedure, what he would like to see. I mean, what are his aims, and what are the objects he would like to see. He would like to see a catheter. Maybe he would like to see a contrast media, even not the contrast media in static forms. He would like to see it flow. So he would like to have a dynamic imaging. He would like to see hit hooks, or whatever he would like to see. You have to figure out together with the operator, are these things matched with what I'm testing? On the right-hand side, you see a typical interventional part. You see a detector, Xray tube, the filtering, the anti-scatter grid. You see the monitor. You see the automatic dose control, and of course, you see the program selector. And many different. You have, as you can see, you have a lot of different angulation and views. You see the detector and the Xray tube are linked to a CRM, and they have one thing in common, and that's the isocenter. You will see that the isocenter will play a prominent role among all testing, and you should see what is the patient anatomy related to the isocenter. I always recommend that the patient should not be very far off the position, very far off the isocenter, because you do all your quality assurance close to the isocenter. But on the other hand, is you have a detector and an angle movement which is very rapidly. So you will see that even though you have an automatic dose control, you also have dynamic move control, and you have a filtering which then maybe changes during the different angulation. And I would tell you that you have to look what are the field sizes you're using, and you see they can differ quite a lot among the area which your system is used in. If you see to radiology, you can go up to 50 centimeters diameters for the detector, and if you look into cardiology, you may not use 50 centimeters in diameter for an image, but you use more. Maybe you use 11 centimeters, and you would like to have the same contrast and the same resolution and the same distortion and the same kV on the same dose by the diameter changed by a factor of 5. So you will see that this may challenge you a little bit more than with conventional radiology. So again, as I pointed out with the conventional radiology, at commissioning stage, meet the application specialist from the vendor, talk to him, and not say only hello. Go into detail. What are the programs and what are the parameters he set? You have to understand your system you're using, otherwise you will fail in quality control. No successful test of the fluorosity system unless you don't know which clinical tasks are going to be performed. For sure. I mean, if you don't see what the system is used for, you maybe test something entirely different to what it is used for. And therefore, again, talk to the radiographers, talk to the operators. What are they doing? What are they aiming at? And invite them to commissioning. I can recommend that. Invite them to commissioning and talk to them how the machine is used. And they should tell you what are the most common performed examinations. What are the most common used fluoroscopy acquisition modes? What are the most common ones? What will they use? And you will see the programs which are preset are, I would say, already overcountable. So it's more than you actually could test. And I can recommend all the settings which are done should be somewhat recorded by yourself. So a very important part is, could you export all the programs which are preset in your system to an external system where you can control the parameter settings? And as I tell that, you ask, it shouldn't be difficult to export settings. Yet still, it is not really pretty easy for the most vendors to get all the settings outside. And you should define one of the programs at your as one of the default program. Default means that is your base program on where you have your baseline very, very well known. And if this program changes due to recommissioning or reacceptance or a breakdown of the machine, Xray tube change, whatever, you should consider that this baseline has to be related to the baseline before, then you know how your values are changed. The architecture of your IRS system is very important. The settings of fluoroscopy and cushion parameters is absolutely mandatory. So you have actually two modes which are given. This is one of the freestanding fluoroscopy and acquisition mode. The fluoroscopy is completely separate from the acquisition mode. This is very simple. The user knows the fluoroscopy mode and has less flexibility. This is almost conventional radiology, where you have fluoroscopy separated from acquisition mode. But if the fluoroscopy is linked to the acquisition mode, then it is more complex, and you really run into some kind of major issues which maybe you have not encountered before. You have to understand how the programs are set, so the acquisition modes. During commissioning, the standard and dedicated programs are set up. That's very important. They are set up. You may have hard times to re-evaluate them during work. So usually they are done in service mode, and I don't know how it's in your country, but service mode access to the machines are usually not given to the users, even so to the physics. What I can recommend is that you can negotiate with the vendor if there's a physics mode, where you actually could have an extra, some kind, I would call it a virtual machine, which is actually the same machine as you use, but it's only in physics mode. It's not a clinical mode, and you can change the parameters, but they will be not changed in the clinical setup. That is something I would recommend for those who are coming into the program to commission a machine. So, but you have to understand what is set. Let me say, for example, you have a fluoroscopic static. So it's a static mode for angio of the extremities. So you have to look what is about the presets and what are the parameters, soft and hard coded. And you will see in the lower right corner, you will see that for DSA2 and DSA3 and DSA4, you have differences in the focus size, and you may have the same KV, but you have definitely different focus sizes used for this investigation. So you see, for different acquire programs, will have a different output. And now we come to the problem: how many of those programs you should be checked? Another problem is you have two machines, same vendor, but they're used differently in two different theaters, but they're still the same. And it could be that on one machine you have a license for, let me say, thrombosis, and on the other, and the other one, I will tell. Sorry, there's a question about the difference between field dose between 16 and 11 centimeters. I will actually give us. I will give doses in the end of my talk. So some example, you have to wait for that. If it's then not answered, please ask again. Then you have to look which licenses are installed. So the vendor is not giving every program free for every user. So if you would like to have electrocardio echography triggering your heart, then it's maybe at the other stage not there, and you don't have a triggered mode. And all these things you have to consider ahead of your use, because if the one machine breaks down and you have to put the one patient to the other machine to get the same intervention, and the preset of the program has another parameters, you will have a hard time to know whether your dose is the same or not. So please ask the vendor that the basic programs should be set with the same presets and the same parameters. And I would actually recommend for that you should get also for that machine a physics mode. So, sorry. Yeah, let me say, let me give you a short example from the Syngo via Simon's interface. This also applies for the Philips Intelligence Space for an angio exam preset. So you have an angio DSA, and in this case, every line which is bold is a basic program, and I can recommend do not change those, because these are your baseline protocols. Because if you change them, all related programs to this base programs are also changed, because they are linked. Depends on the vendor, but usually it is like that. You have a base program, and then for, let me say, extremities of leg or arms, then for maybe thicker persons, or for more bone-like images or more tissue-like images, you will see that the parameters are linked to this base program. So you see that similar parameters are set and they are linked. So what I can recommend is keep the variation as low as possible, but you will see that this is not corresponding to your operators. So you have to find a compromise between the operator's demands and what you set as a physicist. And free yourself from controlling everything. There's a bunch of data, and you could not assure of every program if the settings are appropriate or even optimized. Only look at the most common and frequently one used. Otherwise, you will feel lost. This is actually something what I get from a talk from Professor Marshall from Leuven in Belgium. He is actually given a webinar for the IAAI, and he told us that he have about 800 subroutines for his DSA machine. And if you would like to have checked all the 800 DSA programs, you check the entire day. I mean, you check the entire year and do nothing else than checking all your programs and subparameters. So what I can recommend is look for the most common frequently used programs and check those. And look for a reasonable range of KV and MAS. So what helps us? What kind of tools do we have which easy up our life? So the first one is, which is easy up our life, is the National Electric Manufacturers Association, the NEMA. Here is the international. Here's the AHAPT address in the World Wide Web, where you could find the NEMA report XRS27 or QA mode for interventional radiotherapy. It is something a physicist in interventional radiology should have as his booklet at his breast. I would always say booklet at his breast. You should look into that if you are puzzled or if you are having problems, because this enables you access to all technical parameters behind each button for every vendor. This is definitely a interesting and very broad used booklet. It is free for charge if you have an electronic download. If you would like to have a hard copy, it's about $160. So, and you also, and the good part is you can export the data written in the electronic into a Excel sheet or some kind of text editor program, and you can derive from that your own quality protocol. And the good part is there are comparison tools provided for reviewing and optimizing. I found it rather interesting, and I can recommend everybody working in interventional radiology should have this NEMA standard publication XR727. What are the other ones? What we are going to test? Where it's written. International wise, I could recommend the safety report series number 59 from the IAAI. Even though it's a pilot study, I could recommend have a look on that. And for the EU, there is definitely the radiation protocol 162. This is I would call my actually, for me, it's my revision. So I have to look in that and I will try to get close to what is written there for our national, or even for our national qualification control, quality control. For the national ones, you will find in Germany the DIN 6868-4, and the United States is AAPM report 125, and for United Kingdom is the IAPM report 32 part 8. So all these reports are not free of charge, unfortunately, except the AAPM report 125. The other ones are still you have to pay a fee for that. So, but you see, there are quite a bunch of different guidelines which will give you a hand on what's going to be tested and what is useful. So the first part in your chain is the Xray tube, and for the Xray tube, you'd have to check what is the geometry and your system configuration you're using. As again, there the reproducibility is absolutely essential. I will give you here a setup from Mrs. Türhoff et al. Where you can see how they typically put the phantom in the isocenter, and so and usually the Xray tube and at the lower bottom, and the detector at the higher part. So that would be one possible setup for what you could use. So in physics mode, if you have a physics mode in those cases, you can perform all your measurements, and you have to look that you meet all the local regulatory requirements and the quality control testing to detect degrading of X-ray related components. This is for sure, and you have to have an access of export what you have done. So it's not that you manually write that. So the vendor should provide you with a digital export of the data. And now it comes to two important parts which become more and more getting more and more in the focus, is the radiation dose standard report, the RDSR. The calibration should be put in from the physicist for every field into this report, because they are exported and they are observed by the authorities. And if you put there your baseline in, then you know whether your dose is right or wrong. And for the electronic documentation, you have select something for an XM protocol selection button. This is something you have to, together with the vendors, you should get those reports directly made from your tests. They could be programmed by every vendor. So what are we testing with the Xray tube then? Ideally, it should be tested free from control of the voltage, the current, time, and the focus size. This is not possible unless you put into manual mode. If you have an RDSC or an IAC control, then you will have a hard time to test those. So be sure that in the physics mode or in the mode you are testing, you should put everything into manual mode. Difficult is to set the consistent parameters between the QC fitters. So if you have a manual mode, you really have to be careful how you set your parameters, because this is manual mode and you have to reinstall again all parameters by hand, so manually. So if you look into the NEMA XR27 user control mode, you see what you should test: the tube voltage, accuracy, and reproducibility, the half value layer, and especially with an aluminum sheet, then you should do a KAP calibration. You should look for the field size and the tube leakage. And with the tube leakage, this is also recommended that you, therefore is actually written down in recommendation, is that you have to place a lead shield on the head of the X-ray tube, and the collimation has to be closed. And then you measure at 1 meter distance against the vendor or manufacturing data. That's something this is something which is recommended by the NEMA XR27. The next one you should test is collimate out. So open it. You do to check for the flattening filters, and which can be affected by the voltage and which can affect the anti-measurement. So you check the focus spot size. Then you have to test it in the auto mode. Again, in the physics mode, you have to check whether your physics mode enables also the clinics mode. That is again something you have to check always, that if what you check is also in clinical mode implemented. I would usually protect with a lead shield to protect the TV from the detector. If you're doing that, this is a recommendation. For fully automatic system, you're forced to change the KV. You have to change the KV load behind the KV meter, so you should cover that with copper. It is difficult to do. Make sure that the load is long enough to reliable measurements at 10 and 20 ampere milliseconds. Watch out the pre-programmed spectral filters. So is the spectral filter really inside, and these can affect your tube voltage. Again, thanks to Mr. Marshall. So what do we do then? It's the automatic dose control rate, the RDSC. This is usually a feedback loop controlling the X-ray factors among all other parameters with respect to the change of the patient thickness. That's something what you may know from as the AAIC, so automatic exposure control. Automatic selection of the X-ray factors to cope with the changes in patient thickness as a view of the projection is changed during the exam. Yes. This is something you would like to have. Provide the consistent and image quality. You have to keep the image quality as good as you could. Keep the system operating safely, so technical limits should not be exceeded, and keep the system within the regulatory limits. So don't exceed any fancy positions. Do the ones you know your operator is usually using: LA-045, LA-060, RA-060, or RA-090. These are usually very common angulations. Test those, and not 70.5 degree LAO mid-range or something like that, which is maybe not used at all during the entire examinations. The current RDSC system tries to maintain constant signal in the selected region of the detector. That is what the RDRC is used for. The light output is the energy in the X-ray detector. We monitor the detector input as air camera rate. That gives us constant noise in the image, unfortunately. Noise in the image, not good. System constantly monitoring patient thickness. So you have to, in the system, you know, the water equivalent system. This is what the machine does. The difference between the measured and the requested output is then calculated, and the X-ray factor uploaded for the next pulse. That is what your RDRC is doing. And this could be used for adapting KV and MA and MS for some systems. You can use that. If you would like to have more details how you could do that, see the double APM rate 425. It's very detailed, written there. It would exceed my talk today if I really go into very deep into these details. Yeah. Now we come to the air camera rate. So this is usually microgap per seconds or microgap per frames. This is usually programmed. So this is in the program settings already there. And look what is the most reasonable frequencies of frames you use, and you have usually a very wide range of modes and settings, and you have to figure out which one of those are the one you would like to use. For routine QC, measure the air comma for the common ones, not for any fancy things. And for the ion chambers, you should either use an ion chamber or a solid state chamber. As an example, there's an image to the lower right. Be aware, look what are your ion chambers are actually capable to measure. What kind of dose rate range could they actually measure? To look into that, be aware of the limitations. So here's a setup how we would recommend to measure your air comma. So get the SID approximately at 1 meter or 1.20 meters if you're at the UK. Add anti-scatter grid in or out. Be consistent here. So that means either you put it in or you put it out. If the grid is in, you have to correct for the transmission factor, typical between 1.3 and 1.6. We recommend 2 millimeter copper. We recommend 2 millimeter copper. We recommend 2 millimeter copper for. I'm sorry. We recommend 2 millimeters copper and maximal collimator size. So that should be reproducible. If you open it up, then you know it's always opened. Ensure the detector is out of the sensing areas of the AAC. Sometimes it's hard because the vendor has the entire area as sensing. So what you do then? So far, I have no solution for that. And yeah. This would be the setup I would. What can be used for dose rate displays in the monitors for the periodic? This will come later. I have a slide on that. So what should be tested? Determine which program.
Sir, we will take the question later. You can continue with the slide.
It will be coming later on a slide with something about the dose rates.
Yes, sir.
What should be tested? Determine which programs test frequently most common used one. I will repeat that permanently because it's important. I've seen colleagues testing 150 programs, and I said I'm pretty sure that is not the use of the machine. So look what is the most common one, and then use those. Test both fluoroscopy and anti-equation programs. So what is used for the Xray tube, and what is then needed by the detector. So, and the first one you should check is changes of the air comma visors versus the field of view, and that is something you should check. You should check. Some systems have more than 5 field of view. The most frequent field of views, typical ones I would test is 20 and 25 centimeters. And often they have 3 modes, low, medium, and high, and test those together with the most common FOV to see what you have and what kind of air comma you have. So this is actually out of the talk from Mr. Marshall. This is an example for a sheet of what we actually what you should actually check, or how you would actually proceed. You see in the very top is the measurement setup, the SID, the FAC, receptor position, grid is in or out, fluoroscopy program is written down. Then you look for the seal field size, and then you look for the fluoroscopy program, the kappa filter used, the KV, MA reading, and your output dose rate in micrograde per second. That's maybe answering already one of those question input dose rate you see on the right side, on the right hand side. Then you vary the field size, so the field of view from normal to four of those, and then you have the thickness compensation and the variation of fluoroscopy pulses, so 15 or 30 frames per pulse. So this is one example for a program. It's not that everybody should do that, but that is something which could be done. So, but what are the reference levels? That's something where I actually could say that is something you should be aware of. So the RP162 says for the image receptor Erkmer rate fluorescently normal mode, the suspension level is larger than 1 microgray per second. And the reference for that is the IAPM, so this is the British part. And if you look into the IAPM 95, then you see that the baseline should be better than matched 25%, and the suspension baseline should be then better than 50%. That is what is recommended at the European community. So, what is about the correct settings? I mean, again, what are the field sizes you're using? For example, for a cardioangle system program, diagnostic, no stenting, you have 22 centimeters field of view, and using a frame, a flatness, a flat screen, a flatness, oh God, a flat panel device. So then you will see that it really depends on the manufacturer. And I could advise you, do not hard code those limits and numbers. If you do that and you run over those limiters, the machine may get in trouble. I will answer the combination of frame rates per second and field of view selected good quality images reduce patient dose. Yeah, I will please let me come to this question at the end of the talk again. So entrance Erkmer rate. So fluoroscopy starts with geometry. So first of all, define your isocenter. You think it's easy? Try to start. What is the isocenter? What does the vendor say? Is this the isocenter? So first of all, determine your isocenter. Very, very important. If your isocenter is wrong, all your measurements going to be not good. Then again, look for the mainly common clinical use projection. For example, LA-045. Then look what is one of the SIDs you use, maximum or 120 centimeters. Follow the clinical practice if the grid is used or not. Phantom adapted field size. So if you have a phantom which you're using for, then you should adapt your field size to the phantom and make it not too large or too low. And the skin distance, I would usually recommend 60 centimeters, but you can also use 70, 75. So what is actually recommended for the patient-like phantom materials, tissue equivalent, PMMA, solid water and water itself. Be aware 90 millimeters PMA is approximately equivalent to 100 millimeter water at 70 kV. Cover the entire diameter or the squared field, and the thicknesses you should use of patient thicknesses are 20, 30, and 40. If you're on pediatric programs, I would add 5 and 10. Use in steps of 25 or 5 or 10 centimeters to study the KVMA curve. So this is a typical setup. So your dosimeter is in the is definitely almost in the isocenter, and your phantom is very close to the imager. Then you move, then you increase the thickness and move the table down. So be aware that your device always, that your measuring device is always at the same distance. Again, if you don't do that, it's like this, then make it reproducible what you're doing. So you have to check whether it's reproducible and sensible what you're doing. And
This is to remind you, we have 14 minutes left.
14?
14
Yeah.
left. Okay.
Yeah, I will hurry up a little bit.
Okay, sir.
The next step is rotate to lateral view to see it from the 90-degree side. Move the table to the halfway across the screen and make an image. So what is the expected value? So for the inpatient entrance dose is 100 milligray per minute. It's a suspension level, and the references are given is the EC norm 1975. You see there the baselines are plus minus 25%, 50 milligray per minute or 100 milligray per minute. The RDSC you should actually look for when you commission, then you just adjust for kV, MA, pulse width, a spectral filter, focus size. They could do some nice curving. Image quality is already something we have been talked about with the conventional X-rays. There's really nothing new. The only new thing is that you have to look for the radiation size field, measured size fields, and the spatial resolution on different views. So it could be that the resolution is on 0 degrees, not the same as 90 degrees, and you have to look whether this is correct or not. What we actually recommend for those, there's a clinical setup and a detector setup where you actually look for the detector quality, and the other one is more for the clinical quality, either with the phantom or just with the test object directly close to the X-ray director on the right-hand side. So image quality should be made using commonly used clinical protocol. That's always what I said ahead. They set the clinical pulse rate, the dose level, and the temporal filtration. This is something you really have to set ahead of. Otherwise, you can't compare your results. Remove the spectral filtration so contrast can be estimated accurately. I would recommend is no filtration for image quality. Except you are in the area between 60 and 80 kV, then you should put in these 2 millimeters copper. Viewing conditions are important. That means how do you look on the quality? Again, we talked about room light, room class acceptance test, and the ambient light. No reflection on the screen. Use the variable distance, so 1 meter 50 centimeters far away from the screen. And I can tell you, at the beginning, let's look 2 persons on the same screen and evaluate it, not only one, so that you have more persons looking at what you're seeing. Here's something for the field size, which is actually made with the Leeds Phantom. You see something like a field size versus diameter. Then you can look for the distortion. In this way, you see this image, and then you measure the diameter. And here you see something which is then radiation field, image field with the GAF comic films, and only to let you see that it's possible to do even without electronic devices. Here are the contrasts given. Threshold should be larger than less than 4%. About the spatial resolution is 0.8 lines per millimeters. For field sizes larger than 25, and for field sizes smaller than 25, it should be 1 line per millimeters. That is what actually it's a little bit less than for the conventional radiotherapy. So this was actually everything which I would like to give you. Now we come more to all the measurements you have seen there are static, aren't they? And I didn't talk anything about dynamics. It's always static. So what do we do with the dynamics? And you will see so far in no recommendation, no guidelines, you will have dynamic imaging. Yeah, all objects are static. I mean, are you investigating static humans? No, you aren't. Your patients are moving, and you're changing quality, or you're changing diameters while you are doing images. So all your phantoms should be more close to what you see in reality. So what is the rationale behind? It's hard to say, but you know, a static phantom does not really match the situation you have in your clinical situation. You see that detector tests are definitely more important because you can for the system and for the component performance. But we so far I have only seen quality tests and not quantitative tests, and they should come. And we will give you some hints what should be tested in quantitative. Then 3-day rotational angiography, no tests so far in 3 dimensions, and there is no fluoroscopy system, no specified, there's nothing specified in any guideline. And for the image processing evaluation, so how the images are actually then processed in the on the image side, there's also no testing. What you don't look at the rare data, aren't you? You already you look at processed data. So and everybody who knows about processing of data, you already changed so you should actually look at the real raw data and not on the processed data. And yeah, that is not really something which is evaluated so far. So what are the further steps? The detector currently assessed using test objects. Yeah, that is for sure. Physical evaluation methods are preferred. This is for sure. Not vendor-based or any other physical ones should be. So if you are quite in fluoroscopy and serious for processing images, use the QR27 QC mode. That is definitely something I would recommend to everybody. And brightness and nose uniformity is not tested. Image persistence, temporal resolution is not tested. Noise power spectrum is something you could measure there. If you look into publications, you could do that. Modular transfer function, detector quantum efficiency, you always could check those, and you really have to look whether this could be put into a quality control or not. I would recommend to do so, but there are no standards so far. So what is the take-home message then? Be aware, is the detector evaluation the same as the image quality? No. Detector evaluation is not image quality. But if you have a detector and you know his characteristics, then you know how your final image quality will be. But detector characteristics are not image quality. They are influencing it, but they are not. This is not the same. This is usually very mixed up if I'm going around and talking to persons. So image quality is related to detector evaluations, but the detector evaluation is not image quality. Image quality is definitely more something, it has more parameters than the detector. So conclusion. So make informed, what are your national requirements? Know what your system is used for and how the system works. You have to learn your system. You know how the system is used. And yeah, the NEMA XR27, I think a medical physicist in interventional radiology should not live without that. It's because everything you need is mainly written there. Manual settings should be done for the exposure of the Xray tube. It's not what you should do with the automatic control. Export the parameters and not using something inside. So ask the vendor how you could export your values directly to audit or track your changes, and evaluate your detector very precisely and very, very carefully. And understand the limitation of your device and your quantification methods. Don't try to find something which is far below your scope. I mean, if you would like to find a resolution in our system which is less than 0.2 micrometers to 2 millimeters, you will have a hard time to push your resolution to that point. So be sure what are the deviations from commissioning, and are the commissioning data reasonable or not. And no tests fit all needs. Don't be too disappointed if not everything could be tested. look that you're testing so much as you need for your system and don't push it too far. Be more precise. Quality is better than quantity. So few tests which are qualitatively good are better than 100 tests which are not really good. That's something usually, this is something of my philosophy. So now we come to the end. Thank you very much for your attention. And now we could answer the questions which are coming up. Comments are definitely welcome. And I would like to thank Professor Marshall for this excellent talk in the IAI, which really inspires me for this lecture here. So you will find some of the parts of my talk in his webinar from the IAI, and I can recommend watching this webinar because he is one of the most world-known experts in interventional radiology. So thank you very much. And now we come to the questions. I will open up the chat, and I hope that I
yes, thank you, sir, for your great lecture. And we will look at some of the questions given by the participants. Can I read out?
Okay. How to access the
I think some questions, it was answered like a little bit already, but I'll repeat the question if you can emphasize a little bit more. Can we use the dose rates displayed in the monitors for periodic QC?
First of all, I give everybody my email again. Yes. So if there are open questions left, just write me an email. You're welcome. They will be answered in time, not in seconds. The first thing, so the first, I will scroll a little bit back. So how will we detect the how will we detect the detector quantum efficiency? Yeah, you could do that. Of course, you could do that, but it is not pretty easy. Let me have. Maybe I can show you a good image on that. If I find it directly, I will open it up. Wait a second. Wait a second. I will share my screen again, and hopefully I find the. I have prepared something to that. I have prepared something for that. And sorry. Wait a second. Okay, here we are again. Share. Oops. No, sorry. It's again. So here we are. Here's the. If you look to the right-hand side, there is a. I hope that you can see that there's written gray per frames were those spatial frequency in as a spatial frequency versus the DQA of the detector with a slit size measurement, and then independently on the frames per second.
I'm sorry to disturb, sir. We can't see the slide.
You can't see the slide?
Yeah, we can only see the percentage and front page.
So I will. This person should write me. I will provide him with the information how to measure the DQA. So the person who's then can you please explain the leakage radiation method in CM unit? Pretty easy. You close the slits. You really close them to 0, and then you cover the backside of the Xray tube, and then you measure in 1 meter distance with the highest kV and so the highest kV and the longest exposure you have, in 1 meter distance on the central beam. That would be actually accepted at something which is called the leakage. Leakage to the patient, not leakage to the personnel. The leakage. That's the reason why we cover the. That's the reason why we cover the. I would cover the Xray tube, because that would be dose to personnel. We were looking for the dose to patient, so then we have to look what is actually the leakage through the slit system. But we have to prevent all the other leakage to come into the room and get scattered 3 times. So I hope this was clear. Yeah, 1 meter on central beam, and I usually do also 45 degrees. So an angled angle, but that's depends on what you like. There are actually guys, if you look into the RCR, if you look into the radiation report 162, they have some ideas about that. Something I would recommend. So, but before we use 15 frames per second, so many images per frame. Yeah, that's right. That's something I would also do. That's really okay with me. Okay, then can we use dose rate displayed on the monitors for periodic QCs? Yeah, you have to calibrate them once. You have to calibrate them once during the commissioning, and then you see how your how the dose rates are related to your measurements. But you have to do it once in commissioning, and if you know if it stays there, then you could do that. But it's not what I would do, but I know colleagues doing that. I would actually check on annual basis. So once a year, I would check if the dose rate displays are correspond to what I measure. That's I do that once a year. But it's a good question. You could do that for a trending, but an absolute dosimetry I would do once a year, just to prevent that. Can we use the dose values displayed from the monitor, different machines, hospital centers, duration of national? Yeah, you could do that. Yeah, you could do that, but again, an annual that is not this. You can not get rid of annual measurement whether the value is right or not. You can see the trending, but the offset you don't know, and that's something I would actually recommend to do so. What is the optimum? The combination of frame rate per second or field of view selected for good image quality and reduced patient dose? Not easy to answer because it depends on the patient, pediatric or not. If it's adult, then on the patient thickness, of course, and it depends on. I would call it individual operator factor. That means who's the operator at the machine, and does he is satisfied with your image quality. That's the reason why I said if you would like to look at image quality, let not only one person look on the image quality, let 2 persons look at what they see. I mean, your eyes may see something different than the other ones, and especially person with glasses and without glasses do see differently on image quality. And I can assure you that you should have at least 2 persons looking at your image quality. And talk to your operators again. Very important. If he's satisfied with a low dose image because he could see everything, that's fine. But it's always a matter of how experienced is your user with the low dose images. Some of them are trending to feel they are too noisy. The problem is what would they like to see? Would they like to see the place of the catheter, maybe positioned to the stenosis? That you could also see with definitely less image quality. But again, depends on really what kind of situation you have. There's no really direct answer. Sorry for that. There's no. You really have to have the situation. So why in SYN exposure rates? Why SYN exposure rate is very high? Yeah, that's right. That's true. So that's true. Are displayed doses based on the interventional reference point? Are the displayed dose rates based on the interventional reference point? No, they aren't. They are related to the commissioning, to what you commissioned, not the reference point. So what did you commission for this program and for this parameter? That is what they displayed for. That's the reason why I have a hard time saying this is dedicated to a point. Sorry, for children examination, we can adjust the fluoroscopy with certain settings, or we need fluoroscopy. You need at least filtering, and of course you can do with the adult fluoroscopy you could do to children, but you need filtering because all the you should prevent all the high energies getting into the low energies getting into the kit. So be aware that you need filtering. That is demanded for the EU, and as far as I know, for America, for the Americans as well. So I'm pretty sure that the IAI has also a filtering purifier. Is NEMA free on their platform? Yeah, electronical wise, it's free. If you would like to have a hard copy, you have to pay for it, $160. Can we find patient dose from DAP meter reading? Yes, you can, but it is not easy. Because you need a conversion, you need a conversion factor, and the conversion factors are usually measured during commissioning. So you have usually a factor for the head, you have usually a factor for head and neck, you have a factor for the thorax, for abdominal, and for the extremities. That's something you have to figure out on that you have to figure out what is the patient dose versus the doses area product. There is a conversion factor. And there is also depends on the KV, of course. Yeah, but in the end, you could do that, but you have to do it once. Otherwise, there is a huge there's a huge tabular work from the IAI with conversion factors. If you don't find any, you can write me an email. I will provide you with some older tables from old systems. Are there phantoms to measure temporal resolution in interventional radio? Oh, wow, no, they are so far. You can ask Professor Marshall, actually. He has actually built a phantom for this kind of temporal resolution. I haven't seen it so far, but he wrote me, he told me that, or some person told me that he's providing a publication to that in a short time. In a short time, but there is no unfortunately I have not seen any commercial ones. I have seen individual ones by institutions, but not commercial ones, unfortunately. No, so far not. So did I miss something? Is there any relation between the thickness of the detector and the energy in the photo beam? Yes, there is. Now we come into very detail. Yeah, the vendors are hard to give. I mean, if you look into the NEMA, you find actually some interesting things about detectors, but you know, your efficiency of the detector depends on the thickness of the detector. And so also of the pixel size you're using and the energy which is provided then. There is a relation, yes. There's an old paper from Mr. Christian in 90s, starting of this century, where he dedicated silicon diodes thicknesses versus energy dispersive measurements, and he figured out that there is a dependency which is not constant. It is linear, almost linear, between 30 kV and 120 kV. Below 30 kV is not linear at all, and above 140 kV it is definitely not linear at all. So, but the thickness is then somewhat linear, or at least proportional between those. Okay. a new, okay, please explain frames per second. How, I mean, how many images are taken in one frame? Yeah, that's something you define. I mean, how many images in a frame, that is something which is set in the program. As I told in the beginning, you define how many images are taken in a frame. How many and then you yeah, depends on your program you're looking at. If you are triggering in a heart, then you definitely have more images in a frame than if you are looking for extremities. So that is something you should really that is what I said, you should really into your programs, how many frames and how many images are taken into the frames. And what kind of images is also to say, are the images are fully taken, or only the center of the, or only a region of interest, or the entire image. This is something you also could configure. So if the operator says he would like to have a certain region of interest, then the frame only took the region of interest, even though the detector is larger. That is something you have to define in your program, in the setup. Does it answer the question, hopefully?
I think so. So, and also we missed the very first question, sir. In a flat panel detector, what is the dose difference between 16 and 11 centimeters?
I mean, as you said, Mrs. Yayakodi, they can write me an email.
Yeah, okay.
I will definitely try to answer everything as far as I could in time. So one bit should be a little bit patient, because patient with my answers. It's maybe not in an hour, so, but in a day it should be done.
Yes, sir. Thank you. And also I have one more question. Yeah. Now, when you say that physics mode in the interventional radiology, is it the same like the service mode?
No, it isn't. That's the reason why I said the service mode is usually there, but usually for the service mode, you do not go get access, because the companies do not, or the vendors do not like that physicists try to fool around in the service mode. That's a reason why I recommend to talk to the vendors if they could give you something. I would call it a virtual machine, which is close to the clinical machine, but it's not for clinical use. So you can use all the parts which are used for clinical use, but you have a little bit more access to flexibility of KV, MAS, so you really can set manually those things and not try to have to use a pre-programmed sets of parameters. Yeah, but it's not usually there. It's not usually, you really have to but I mean, if you, it depends really on your local vendor. If they are I already had the experience that if they figure out that the physicist is experienced enough, you could get attached to the service mode. You could do that. But I'm not a good friend of service mode to physicists, because we figured out that if you change something there, you change the entire setup, the parameters, and you have to be extremely careful what you're doing. If you are fooling around in the physics mode, you do not influence the clinical and the service mode. That's something I figure out it's very valuable. But you know, if you are experienced enough and you feel secure, maybe your manufacturer try to give you some kind of service mode. I mean, I have seen everything so far, but I'm definitely a friend of the physics mode. Definitely I am, because then I'm free of being careful and become more experimental. So you can do a little bit more, and you can harm, but still you can harm the machine. So you really can ruin the machine in the physics mode if you go to extendedly emitted. That's for sure. That's something you could do, but it's not as easy as in the service mode, because in the service mode all limits are actually opened, and the dose control is opened, so you can choose 2 gray per minute. I don't like that. I mean, I'm not a friend of 2 grays per minute, actually. I mean, somebody would like to do that, but I don't like that. But it depends on how you agree with your vendors. But the physics mode is actually a good part also for trainees. So for a person who needs to be educated, they can actually, you can give them a project, and then you say, okay, you log in physics mode, and then you try to change the KV from 30 to 112, and you look for the exposure symmetry or homogeneity, or you look for the value if you are changing the filtering. So that's easier for education. I mean, it's important. And as a university hospital, I have to educate persons. And the physics mode enables me to give the students a little bit more access to the machine, if they are willing to come after 8 o'clock in the evening. Okay, I'm sorry.
That means like what you're saying is it's a safe mode that we can do more research rather than just opening up like the service mode.
Yeah, of course.
Yeah, okay.
That is what to do. But the problem is some vendors do not like that you do research on their machines, because you may find things which are not good enough. I mean, if you already have, or if you ever had a machine which has a better release, so you get a release where you should test clinical some applications for the vendors, and if you have done that, and then you see that it's not fully evaluated, and then you see some parameters are not in spec, and you're not allowed to publish that because it is confidential, then you see the reason why. Some vendors are very restricted to that, and I mean, if you are living close to the vendors, like in Erlangen in Germany, Siemens has a huge factory there. Of course, the person from Erlangen have very good access to the beta or alpha releases, but we do not. So we have a hard time. So the physics mode enables us to have a little bit more research on what I would call future developments, like looking for the modular transfer function, for example.
Yes, thank you, sir. Can I ask one more question in that same side? Now, in case if you are trying to get the physics mode to your facility, what will be the vendors looking at? I mean, like what type of conditions will they look at? Whether the capability of the medical physicist?
Oh, yeah. Oh, it's not an easy question. I mean, what would they look at? Especially combinations of voltage and focal size, for example, or current and kV and focal size, and look whether in what kind of minimum and maximum SIDs you could actually vary your. I mean, how close could you get the detector to the patient? And so geometry is definitely the thing they're looking at, and then the flexibility of your parameters like voltage, current, focal size, time. That's focal spot size. That's really something they look at. They are not interested in modular transfer. They are not interested in modular transfer function or DQA. That is not something they're really interested in. If you ask for that, you should ask persons who are actually doing research on that, and then you find persons which help you to access those values easier.
Yes, thank you so much, sir. And we just got one more question.
Yeah, okay. Is there include cine time and fluid time that shows on screen after finishing procedure? Is there? Yeah, it should be actually. I don't know. That's an interesting question. I don't know how it's in India or Bangladesh. I don't know that, but in Europe it is mandatory that the vendor has to show the cine time. I don't, but I know that is related to the regulations from the authorities, whether they have to show or not. I know that among the EU they have to show the exposure time, so the cine time and the fluoroscopy time. That's something they have to show. The funny part is they're showing the time they have measured. It's maybe not the real time of online. That's the reason why you should do QC. This is the reason why you should do quality control, to check whether the time they measure the same time is the beam is on. Because switching off of a pulse beam is very interesting to see when they switch off and when they switch on, how many pulses they take. That's very interesting to see. So yeah, you should see us, but be aware the time they show is not the time of beam on. That's my personal, it's a personal opinion. I can't really prove that for all machines, but I have seen machines where the beam on time shown by the vendor is different to what actually is the actual beam on time is.
I think that is all, sir. So thank you so much for answering the questions, and also I think your lecture was really interesting. And also I think I saw in one of these chat also your philosophy, the quality is better rather than taking more scannings. That is your philosophy. I think we all agree with that. Yes, thank you very much, sir. And also before ending, I would like to thank the chairman of SCMPCR, Professor Dr. Ghulam Abu Zakaria, and entire team of SCMPCR whose effort have made this session very successful. And thank you for all participants who joined today also. We appreciate your presence. And also our next lecture will be on 18th Friday, and it will be about CT dosimetry and reconstruction of augmentum. Dr. Ghulam, would you like to talk?
Yeah, I just a moment of comments. Thank you, Stefan, for the excellent.
Yeah, hi, Abu. Welcome, welcome, Abu.
Excellent presentation. You are one of the few expert in radio diagnostic. Of course, you are very good in also radiotherapy. Both are you are very good. He's actually one of the few examiner in Germany for our qualified medical physics. So you can ask him anything what you like. He's also very dear to his students. And he has given you also some guideline here, some international protocols. Please read these protocols. You can download these protocols and you can find the guideline to do quality control in interventional radiology. Interventional radiology is not easy, yeah. That's why medical physicist is joined in this area. The medical doctor is not enough to sustain the quality. But what Dr. Garbe told, you should understand actually how the machine functioning, what is his job. And so a very good cooperation with medical doctors, even technician. So when you have a good relation with medical doctors and technician, you learn from their perspective, and you are the scientist, and you can do then the quality control is very well. Actually, it is not easy quality control in radio diagnostic. I think it is more difficult than radiotherapy, but it is because, and especially in interventional radiology. Please do your best and try your best, and it is our job, and we should have a very good quality control to save patient and ourselves. Thank you, Stefan, for taking time, and and we see you again in SCMPR or other international forum. Yeah, we want to see you again and again. Yeah, thank you.
Okay, thank you very much, Abu. Thank you very much, Mr. Yakakodi, for the moderation. I appreciate
very nice moderation. Yeah.
I appreciate your moderation. Thank you very much for that.
Her name is Joya Kudi. Yes, Joya.
Thank you.
But in German, J is yeah. That's why Yakodi. No problem. So you have done also very good job. Thank you once again. Yeah. Thank you.
Thank you, sir. Thank you so much, sir. Thank you, everyone, all the participants, and thank you and stay safe.
Yeah. Goodbye.
Thank you all. Goodbye.
Goodbye. So Shimanto, thank you. Goodbye. And your staff.